Hello everyone. So we were learning colligative property under the chemistry of dilute solutions, and our today's topic in the third lecture are Clapeyron Rule and the Clausius-Clapeyron Equation. We had four colligative properties such as lowering of vapor pressure, elevation of boiling point, depression of freezing point, and osmotic pressure, out of which for the next two properties which we are going to discuss in the lecture number 4 and 5, for that two equations would be required very much. One is the Clapeyron equation, another is the Clausius-Clapeyron equation. So with the help of these two equations, the derivations of these two can be made. That is why we have got to learn these two things prior to understand regarding the topic elevation of boiling point and depression of freezing point. So let's start from the Clapeyron equation, and for that we have to take help of the fundamental thermodynamic equation, where we have to use the expression of dg, and the expression of dg is v dp minus s dt. We all know about this. This is the fourth fundamental thermodynamic equation. Now suppose there is a system which is in state 1, or that is one of its phase, maybe it's solid, liquid or vapor. Now it changes its state from state 1 to state 2. Okay, that may be some another state. If it's a solid, then it may be liquid or vapor. If it is a liquid, then it may be a solid or liquid, and so on. So if a substance is at state 1 and is at equilibrium with its another state, say the state is state 2, then for an infinitesimal amount, that means there is a very little bit amount, okay, of the substance which converts its phase from state 1 to state 2, then the free energy change due to this phase transformation. What should happen? In one of the phases the free energy would decrease, and in another phase the free energy would increase. So these free energy changes may be written as minus dg1 and plus dg2. Okay, and if we try to take help of this equation, then dg1 should have its own expression like v1 dp minus s1 dt, and dg2 would have its own expression like v2 dp minus s2 dt. So the respective expressions of dg1 and dg2 are here written: v1 dp minus s1 dt and dg2 equals to v2 dp minus s2 dt. At equilibrium, minus dg1 plus dg2 should be equal to 0, because at equilibrium dg1 is equal to dg2. So the right hand sides of these terms, dg1 and dg2, would also be equal. So let's equate the right hand sides of these two expressions also. And the right hand side of dg1, that means the expression of dg1 is v1 dp minus s1 dt, and the expression of dg2 is v2 dp minus s2 dt. Now the dp terms are taken in the left hand side, and in the dt terms are taken in the right hand side. As a result, we get the expression v2 minus v1 dp equals to s2 minus s1 dt. And if this expression is cross multiplied, then we shall get here dp by dt equals to s2 minus s1 by v2 minus v1. And this s1 s2 minus s1 may also be written as delta S, that means change in entropy. Now if temperature T is multiplied in the numerator as well as in the denominator, then this there would be no change actually. So let us multiply temperature T in the numerator and as well as in the denominator also. Then we shall get the next expression, which is dp dt equals to T delta S divided by T into v2 minus v1. And here we are mentioning that multiplying both numerator and denominator by temperature T. Now we know the second mathematical form of the second law of thermodynamics, where we say that if Q is reversible in nature, then Q by T is change in entropy. So here Q is reversible molar heat of phase transformation. That means it may be latent heat of vaporization, it may be latent heat of sublimation. So this is the molar heat of phase transformation at temperature T. T means that corresponding temperature. If it is vaporization, then it is boiling temperature. If it is sublimation, then it's sublimation temperature. In that case, we know from the second law of thermodynamics that delta S equals to Q by T, or conversely T delta S equals to Q. Okay, so in place of this T delta S, we may put here Q, and thus we get the expression dP by dt equals to Q divided by T into V2 minus V1, and this is known as the Clapeyron equation. Okay. Now the significance of the Clapeyron equation. So where we can apply them properly. According to the Clapeyron equation, the rate of change in pressure with respect to temperature or vice versa. That means here, look back here. This expression is dP by dt. That means what? This is the rate of change in pressure with respect to temperature, and vice versa also. If it is dt by dP, that means if you reciprocate this equation, then this part would go to the numerator and Q would come to the denominator. In that case, the rate of change in temperature with respect to pressure. Okay. And here, that thing, the second part is mostly utilized because you are changing the pressure and the respective phase transformation temperature is also changing. Suppose pressure is increasing, boiling temperature increasing, pressure is decreasing, boiling temperature is decreasing. So this can be explained mathematically with the help of the Clapeyron equation. So let's check. So according to the Clapeyron equation, the rate of change in pressure with respect to temperature or vice versa is this one. Here in place of Q, you can write delta H of transformation. That means the heat of phase transformation, and the corresponding temperature. If it is vaporization from liquid to vapor, then this is boiling temperature. So if you write transformation, then it would cover generally the all type of phase transformations. Okay, and this is V2. That means after the transformation taking place, the volume of the state 2, and before the transformation taking place, the volume of the state 1 is V1. Okay, so here delta T transformation is nothing but Q, which is the enthalpy change due to first order phase transition. These phase transitions are actually first order phase transition because they are involved with latent heat. If there is no latent heat involvement, then they are second order phase transformations. Okay, so these phase transformations have the examples: heat of fusion, heat of vaporization, etc., or heat of sublimation, etc. TR is the respective temperature. If it is fusion, then this is the melting temperature. If it is vaporization, then it is the boiling temperature, isn't it? So TR is the phase transformation temperature. Okay, and V1 is the volume of the initial phase, while V2 is the volume of the final phase. That means after the phase transformation taking place, the volume becomes V2 from V1. Number 1, for liquid to vapor phase transformation. So we are dealing with the liquid to vapor phase transformation. That means we are dealing with the vaporization of a liquid. In that case, the temperature is actually the boiling temperature TB. Q is actually heat of vaporization, that means delta HVAP. V2 is the volume of the liquid, that means the second phase. Okay, that means the volume of, I'm sorry, not the liquid, the volume of the vapor, that means the second phase. Okay, and V1 is the volume of the liquid, that means the volume of the initial phase. In that case, that Clapeyron equation gets the form. Here in place of Q, you write here delta H vaporization, and in place of T, you write TB, and in place of V2 you write V of the gaseous form, and in place of V1 you write V of the liquid form. So this equation may be utilized if it is a liquid to vapor equilibrium. Secondly, for a solid to vapor phase transformation, this is actually nothing but sublimation. So in that case, temperature is the sublimation temperature. The heat change is actually the heat of sublimation. The V2 is the volume of the vapor phase, and V1 is the volume of the solid phase. In that case, this Clapeyron equation may be converted into this one. So in that case, we get dP by dt equals to del H sublimation divided by temperature of sublimation temperature, into volume of the gaseous form minus volume of the solid form. Okay, you try to find the significance of these two equations here. Here delta H is actually for liquid to vapor transformation. Delta H is positive because heat is absorbed here, isn't it? And here Vg is definitely greater than VL, so this is a positive parameter. Okay, this term is positive, so dP dt is positive. That means P and T are directly proportional to each other. So if you increase the pressure, then boiling temperature could increase. And try to find out the example. Suppose water boils at 100 degrees Celsius at 1 atmospheric pressure, and if you try to boil water at that hilltop, that means some higher altitude, their air pressure is lesser. In that case, water boils at less temperature than 100 degrees Celsius. Similarly, in case of sublimation also, here this parameter is positive. Okay, this is positive term, because here also heat is absorbed in case of sublimation from solid to vapor, and this Vg is definitely very much greater than Vs. As a result, this is a positive term, and dP by dt is positive. That means pressure is directly proportional to temperature and vice versa. That means if you increase the pressure, then sublimation temperature would also increase. Now the Clausius-Clapeyron equation, with the help of the Clapeyron equation, let's take as for example two examples. One is liquid vapor equilibrium, another is solid vapor equilibrium. Mainly these two would be utilized in our colligative property discussion. So in both the cases, the V2 is much more greater than V1, because a vapor has the volume which is much more greater than the volume of the liquid or the solid. So in both the cases, V2 is much more greater than V1. That means V2 minus V1 is almost equal to V2. That means the volume of the final phase, that means the vapor phase. Therefore, we can convert this equation as dP by dt equals to Q divided by T into V2 minus V1. Here we are writing V2, and in place of V2 we have written the ideal gas equation. With the help of ideal gas equation, we have obtained V2 equals to RT by P, because PV equal to RT or PV2 equals to RT, so V2 must be equal to RT by P. So in place of V2 we have written here RT by P, and after rearranging, this P goes to the numerator and RT remains in the denominator, and as a result you get the final form Q into P divided by RT square. So this is the expression of dP by dt for these two types of equilibriums. Okay, now take the P related terms in the left hand side and other T related terms and the constants in the right hand side, and let's integrate this relationship dP by P equals to Q by R into dt by T square. Here Q by R is are constants, and these two are the variables, pressure and temperatures. So integrating both sides, giving limits. What should be the limits? The pressure should be P1, final initial pressure, the final pressure should be P2. Okay, the initial temperature should be T1, the final temperature should be T2. That means, suppose you are trying to boil some water, or you are trying to sublime some solid, suppose naphthalene or camphor, whatever. So at some initial pressure P1, its sublimation or boiling temperature is T1. At some other pressure P2, its respective sublimation or boiling temperature is T2. Okay, so these two can be the limits of the integration. So integrating both sides of this equation, integration P1 to P2 of dP by P equals to the constants Q by R into integration of T1 to T2 into dt by T squared. Okay, so what should be the result? The result is natural log of P2 by P1 equals to minus Q by R into 1 by T. If you put the limits, then it becomes 1 by T2 minus 1 by T1. This minus can be adjusted here by writing 1 by T1 minus 1 by T2. Now look what happens for liquid to vapor equilibrium. In that case, Q is heat of vaporization. Okay, hence the equation can be written as, for a liquid vapor equilibrium, ln P2 by P1 equals to delta H vaporization by R into 1 by T1 minus 1 by T2. And number 2, for, let's block this before that, and number 2, for a solid vapor equilibrium, Q may be substituted with delta H sublimation. Okay, and the expression, other things are same. ln P2 by P1 equals to delta H sublimation by R into 1 by T1 minus 1 by T2. So these two are the final forms of the Clausius-Clapeyron equation, and let's plot them. Okay, and another thing we have to utilize in deriving elevation of boiling point and depression of freezing point, particularly for depression of freezing point, we got to use this relationship also, because delta H is an additive property according to the second law of thermochemistry, that means the Hess's law. Okay, solid to liquid, delta H of fusion, liquid to vapor, delta H of vaporization. So direct from solid to vapor, it is, if it is delta H of sublimation, then according to the Hess's law, what? That is delta H of sublimation equals to delta H of fusion plus heat of vaporization, or delta H of vaporization. Okay, so this equation would also be utilized. So that's all for today's lecture number 3. Thank you and have a nice day.